Hey there, fellow data enthusiasts. Welcome back to another exciting video on our channel. Today we have a topic that will take your data analysis skills to the next level. We will be exploring the powerful world of zonal statistics using Python. So grab your favorite beverage, sit back, and let's dive right in. Have you ever wondered how to extract meaningful insights from the raster data? Zonal statistics comes to the rescue. It allows us to understand how values in the raster dataset are distributed within the predefined zones or regions of interest. Whether you are working with the environmental data, satellite imagery, or geographical information system, zonal statistics is a fundamental tool in your data analysis toolbox. Let's say we have a raster dataset representing rainfall values across a region. With zonal statistics, we can calculate the average rainfall in a specific zones like districts, neighborhoods, or any other defined regions. Alright, the first step is to open the Anaconda prompt. To do that, simply search for the Anaconda prompt in your Start menu. Now that we have the Anaconda prompt window open, it's time to type the command that will open Jupyter Lab for us. In the Anaconda prompt window, type the following command: Jupyter-Lab, and hit enter. Now that we have Jupyter Lab open, on the left panel you will find the File Explorer where you can navigate to New and click Notebook where you can create your new notebook. The main working area is in the center where you can create and edit your notebooks. In this video, we will walk through the practical implementation of zonal statistics in Python using some popular libraries such as rasterstats and pandas to get the job done efficiently. Now it's time to put our Python skills to work and implement zonal statistics on a real dataset. We will be using Python libraries such as rasterstats and pandas to make our data analysis a breeze. First things first, importing necessary libraries required for zonal statistics. Import pandas, geopandas, rasterio, rasterio.plot import show. From rasterio.plot import show ist for histogram. Import rasterstats to perform zonal statistics. Import matplotlib.pyplot for data visualization. Once you enter the details of the libraries, click Run to execute the code. We will define our zones using some geographical boundaries such as administrative districts or custom defined regions or grids. In order to read grid shapefile, one has to use the read_file function from the geopandas library in Python. This function is used to read various geospatial file formats and create a geodata frame, which is a pandas data frame that includes geometry information. To use the read_file function, you need to provide the path to the geospatial file you want to read as an argument. Once the zones are defined, we can calculate the desired statistics such as mean, minimum, maximum, and more for each zone. Next, we use the rasterio.open function to open a raster file in Python using the rasterio library. Rasterio is a powerful library for reading and writing geospatial raster data. In this code, we are importing the rasterio library, providing the correct file path to the rasterio.open function. And specifying the mode as or to open the file in read mode. Once the raster file is opened using rasterio.open, we can work with the raster data using the methods and the attributes provided by the RF object. To get started, we will assign the raster values to a NumPy array. This line reads the raster data from the opened raster file RF and stores it in the rainfall_array variable. The argument 1 specifies that want to read the first band of the raster data. Raster data can consist of multiple bands, each representing different attributes such as red, green, blue in a satellite image. In this case, we are reading the first band. Affine is equal to rf.transform. This line retrieves the affine transformation matrix from the opened raster file and stores it in the affine variable. The affine transformation matrix is used to convert pixel coordinates to geographic coordinates and vice versa. It includes information about the rotation, scaling, and translation of the raster data. After running these lines of code, we will have the rainfall underscore array containing the actual raster data values from the first band of the raster, and the affine transformation matrix that can be used to georeference the raster data. Then we will calculate the zonal statistics using the rasterstats library. This powerful library allows us to extract statistical information from the raster datasets within specified zones. In order to perform zonal statistics, we are using rasterstats library on the rainfall underscore array using a set of zones defined in the GeoJSON file specified by fn underscore zones. And the argument affine is the affine transformation matrix that relates pixel coordinates to geographic coordinates. It is used to properly align the raster data with the zones defined in the GeoJSON file. And the argument stats is the list of statistical measures which we want to compute for each zone. The list we provided includes mean, minimum, maximum, median, standard deviation, and sum. Finally, GeoJSON underscore out is a parameter indicates that the output to be in GeoJSON format. After running this line of code, the rainfall variable will hold a list of dictionaries, each containing zonal statistics for a specific zone. After calculating the zonal statistics, we will extract the results into a list. This list contains information for each zone such as the mean, minimum, maximum, median, standard deviation, and sum of the values within the zones. To make our analysis more efficient, we will transfer this information into a pandas data frame. In order to extract the zonal statistics results from the rainfall list and store them in the avg underscore rainfall list, use a while loop to iterate through the rainfall list and extracts the properties dictionary from each element. It iterates through each entry in the rainfall list, which contains the zonal statistics results for each zone, and appends the properties dictionary from each entry to the avg underscore rainfall list. The properties dictionary likely contains the computed statistics for each zone. Using the power of pandas, we are able to perform various data manipulations, visualizations, and further analysis effortlessly. This allows us to gain deeper insights into the patterns and trends within our data, enabling informed decision making. In order to update the zonal statistics attributes to the shapefile, it is iterating through rows in the data frame named fn underscore zones and updating attributes based on the statistics from rainfall data. This loop iterates through each rows in the fn underscore zones data frame. The loop variable I represents the index of the row, and row is the data within that row. Stats is equal to rainfall I for properties. This retrieves the statistics dictionary from the rainfall data for the current index I. While rainfall is a list of dictionaries, each containing the calculated statistics for a specific zone. For stat underscore name, comma, stat underscore value in stats.items is a nested loop. It iterates through the key value pairs in the stats dictionary. The keys are the statistic names such as mean, minimum, median, and the values are the corresponding statistics values. fn underscore zones dot at I comma stat underscore name is equal to stat underscore value updates the attributes in the fn underscore zone data frame for the current row and the current statistics. It sets the value of the attribute named stat underscore name to the corresponding statistic value. Finally, we have calculated zonal statistics and updated attributes in the geodata frame fn underscore zones, and now we want to save the changes to a new shapefile. To do so, we declare a variable called output underscore path. This variable holds the file path where we want to save the new shapefile with the updated attributes. Now we use the to underscore file method of the geodata frame fn underscore zones to save the data to the specified output path. The method automatically determines the file format based on the extension which we provided. It creates a new shapefile with the updated attributes. In order to verify the updated shapefile, select the file with .shp extension in the directory. Drag and drop it in QGIS layer panel. Once the file imported, select the layer and right click on it. Then select Open Attribute Table. Here the layer attribute table has been successfully updated with zonal statistics data. To verify the empty records, click on the column address for sorting and identify the respective record. In order to select respective records, click on the specific row on the left side of the attribute table panel. Minimize the window and zoom to yellow color highlighted grid. We are going to create a subplot with two plots using matplotlib library in Python. We have an imagery plot of rainfall data along with the boundaries of zones on the left side and a histogram plot on the right side. Finally, we are going to export a geodata frame containing zonal statistics attributes to an Excel file. This can be helpful for further analysis or sharing the results. To do so, we're going to declare a variable called output underscore Excel file. This variable holds the file path where we want to save the Excel file with the zonal statistics attributes. And Tamil Nadu, this represents a geodata frame containing the zonal statistics attributes. The to underscore Excel is a method is called on this data frame. This method exports the data from the geodata frame Tamil Nadu to the specified Excel file path. The index false is an argument ensures that the data frame index is not included in the Excel file.